I would like to very much thank the organizers for having me here at this very nice workshop. So here in this talk, I will tell a story about unconventional pinch points and how quantum effects act on them. Okay, so in the bulk part of this talk, I will present this recent paper together with my PhD student, Niels Niggemann and Yassir Iqbal. And then in another part of this talk, I will very briefly talk about very recent activities together with Björn Spierski and Benedikt Schneider, who are here also somewhere. Okay. So pinch points are associated with gauge theories. So I will first of all give an introduction to classical spin liquids as realizations of gauge theories. Roderich already prepared the ground here, but I will still give a brief introduction here. Okay, the well-known example, which Roderich already mentioned, is the 2-in, 2-out spin ice rule for low energy states in Ising pyrochlore magnets. So in each tetrahedron of the pyrochlore lattice, 2 spins have to point in and 2 spins have to point out. And this can be written as an effective Gauss law, as shown here, if you identify the spins with an emergent electric field. And then it's actually only a few steps of calculations to show that this leads to sharp pinch points in the electric field correlator and algebraically decaying spin correlations. Okay, if this 2-in, 2-out rule is violated, then it means the divergence is no longer 0. For example, this happens if I flip the center spin here. So this then creates 2 defect tetrahedra in these 2 tetrahedra. And we say that they carry charge, or one can also call it a spinon, or depending on your convention, one can also call it a monopole. And this is conserved and gapped. And the presence of such charges now means that the pinch point typically becomes broadened and spin correlations decay exponentially. So far, this is just an effective electrostatics theory. Now, let's include quantum fluctuations. For example, one can do that by changing the Ising interactions to XXZ interactions. So adding this term here, and particularly if delta is small, one can treat it perturbatively, and then one ends up with a U1 quantum spin liquid, so an emergent quantum electrodynamics with all its associated phenomena, for example, an emergent photon quasiparticle, which also has linear dispersion. And now actually the consequence of this photon branch is that the electric field correlator is modulated by an extra factor omega at t = 0. But since omega vanishes right at the pinch point, it means that the pinch point is linearly suppressed here at the center. Okay, now let's generalize this towards what I called unconventional pinch points. Particularly, we generalize this type of gauge constraint towards this one, where we now have 2 derivatives acting on an electric field. And the electric field is now a tensor, a matrix, to be more precise. And now one can actually show that not only the charges are conserved, but also the dipole moment. However, the dipole moment is responsible for the mobility of charges. Yeah, so that can be easily illustrated. Let's consider an isolated charge here, and let's assume we want to move it to the right. What we actually do here is we add a dipole moment here. So this means that here positive and negative charges cancel, such that the charge has effectively moved to the right. And we can repeat it once more. And it has again moved to the right. However, if now the dipole moment is conserved, it means we cannot just add this dipole moment here, or in other words, we cannot move this charge. So this then leads to a new kind of immobile quasiparticle, which is called a fracton. It's a type of quasiparticle which has not yet been observed, but only theoretically envisioned. Actually, in this picture, which I present here, it's a so-called type 1 fracton. So type 1 means that there are still composite particles which can still move along 1D lines. They are called lineons. Actually, the dipole moment itself is a lineon. Yeah, if you think this idea here a bit further, then you can show that the dipole moment can still move perpendicular to its vector direction. Okay, and now the consequence of this new Gauss law here is that there are now fourfold pinch points in the electric field correlator. So 4 lobes of strong intensity. And the rest of the story goes very similar as before. So the presence of charges in this schematic picture here means that pinch points become smeared. And also one can make the theory quantum. Then also one obtains photon excitations. In many cases, the dispersion is also linear. And overall, one ends up with a theory which is called rank 2 U1 quantum electrodynamics. And also as a consequence of this photon branch, the electric field correlator gets modulated with an extra factor of omega, which again suppresses the pinch point here in the center. So far, all this here is completely independent of any spin model. But of course, the question that arises is, are there any spin models which realize this situation here? So to say higher rank generalizations of pyrochlore systems. And the answer is yes, at least on the classical level, there exist quite a few models. And the one we consider here is the so-called octochlore model, which has first been proposed here. So it's a model that is based on an octahedral lattice. So it consists of corner-sharing octahedra, and this is the Hamiltonian. It's a sum of squares, where the sum goes over all these clusters. And under the square, we have a sum over all spins in the cluster, but differently weighted. Yeah, this is color encoded here: green, dark blue, and light blue. And now it's clear a classical ground state is realized whenever all these squares here are 0. So one can calculate a classical ground state phase diagram. And actually the full phase diagram only consists of classical spin liquids, so extensive ground state degeneracies. And now it's actually interesting what happens at the phase boundaries. So for example, here, one encounters a multifold pinch point of rank 3. I will come back to it later, with 6 lobes of large intensities. By the way, here I plot the spin structure factor, which is basically proportional to the electric field correlator. So a quantity which in principle you can also measure in experiments. Then here at this point, you obtain an even more exotic type of pinch point, the so-called quadratic pinch point, where the contour lines are parabolas. And these have been associated with type 2 fractons. And then finally here, one finds a so-called pinch line singularity. So here the pinch points do not form isolated points in momentum space, but they occur along a full And since I'm using these terms type 1 and type 2 fractons, again, type 1 means that composite particles exist which can still move along 1D lines. However, in type 2 fractons, all quasiparticles are completely immobile. Okay, and now what our work is about is to investigate the corresponding quantum model where the spins are now spin 1/2 objects. And we ask the question, for example, do the pinch points survive in this quantum limit? Actually, this in a way generalizes questions which have previously been asked for the pyrochlore-Heisenberg model. But there is now growing consensus that, okay, first of all, it's non-magnetic, but still with broken lattice symmetries. So it could, for example, be a valence bond solid. Okay, it's also clear that if we want to treat this model numerically, this is very complicated. Yeah, it's a complicated 3D model, highly frustrated. but we think we have very powerful methods at hand which can tackle this model. Okay, this brings me to the methodological part of this talk. Here I will very briefly introduce our two methods, PFFRG and PMFRG, which stands for pseudo-Fermion and pseudo-Majorana functional renormalization group. And in this context, I would also like to advertise our brand new review article on these two methods, which just appeared last week, Friday, on arXiv. Okay, so let's start with PFFRG. There we need pseudo-fermions. We start with some type of two-body spin Hamiltonian, and we first express the spin operators in terms of complex fermions, so-called pseudo-fermions. Yeah, so this is this typical fermionic mapping of spin operators. However, of course, right at the beginning, there is something to be very careful about. This mapping enlarges the Hilbert space with unphysical non- and doubly occupied states. From our experience, it seems that in many systems, unphysical states are excitations. That means that it's still kind of justified to apply the method at least at t equals 0. However, it's also well known from this paper here that there are exceptions. Yeah, so this the enlarged Hilbert space is definitely a caveat of this method, which one has to keep in mind. But I will also show you in a moment how one can actually do better. But once one has accepted this mapping, we plug it into our Hamiltonian. We end up with this Hamiltonian, which is now purely quartic in the fermions. And now we can do Feynman diagrammatics in the fermions. So we define a propagator and an interaction vertex. And now actually the magnetic response functions we are interested in, they correspond to this two fermion scattering amplitude. So it means in principle, we would have to sum up all kinds of diagrammatic terms which contribute to it. So what I would like to illustrate with this here is that in our understanding, it boils down to some kind of sampling problem for Feynman diagrams. And now it's known that FRG provides a very efficient resummation scheme for Feynman diagrams. However, it doesn't generate diagrams term by term as indicated here. Yeah, but maybe in a very oversimplifying way of phrasing it, one can say that FRG sums up large classes of Feynman diagrams, so to say, continuously during the flow of an RG parameter lambda. So as lambda is varied between two limits, so to say, large classes of Feynman diagrams are switched on continuously. Or to be more precise, RG parameter lambda can be implemented as a low frequency cutoff in the propagator, for example, via such a step function which switches off small frequencies. And then essentially RG boils down to a set of differential equations for all kinds of vertex functions, which is infinitely long and first of all exact, but in order to treat it numerically, we have to truncate it. This is typically done at the 3-particle level, or more precisely, we often or typically apply a truncation which has first been proposed by Katanin. And if we implement this scheme with our pseudo-fermions, then we end up with the PFFRG. Okay, now alternatively, we can also do the mapping with Majorana fermions. This is shown here. So spin operators are expressed in terms of these C Majorana fermions, which square to 1. And this actually now has the huge advantage that there are no unphysical states, only redundant Hilbert spaces, but that actually doesn't pose a problem for us. So if we do this scheme with Majorana fermions, then we obtain this approach, which we call pseudo-Majorana FRG, which now can also be applied at finite temperatures. And building up on earlier works, very recently, we have also developed a scheme where the temperature itself actually plays the role of an RG parameter. So this is so-called temperature flow FRG. It has a higher efficiency because we don't need to run a separate calculation for each temperature, but one RG run already covers all temperatures. So in summary, the approaches we apply is PFFRG at t equals 0, PMFRG at finite t with lambda flow, and PMFRG at finite t with t flow. Now let's do a little demonstration of the capabilities of this method for the antiferromagnetic Heisenberg model on the simple cubic lattice. Yeah, we know its properties. It should form this type of magnetic Néel order. And in order to find this type of order, we perform T-flow, PMFRG, and we look for critical finite size scaling. So we know right at the phase transition, the correlation length should be proportional to the system size. And this is shown here, correlation length divided by system size as a function of temperature for different system sizes. And we indeed find a well-defined crossing point here at the temperature, which is actually incredibly close to the quasi-exact quantum Monte Carlo result. And I think this is quite a nice result here. But we can also add frustrating interactions, which quantum Monte Carlo cannot do, like a J2 interaction. It acts here on the phase diagonal. And the classical phase diagram has a phase transition at a coupling ratio of 1/4 to this type of order with wave vector 0, pi, pi. And here is our data, critical temperature as a function of J2. It's actually hard for us to reach very small temperatures, but we can still kind of extrapolate these lines. And it seems that there is either a small disordered phase here or the two magnetically ordered phases just meet. And okay, there are not many results in the literature to compare this with, but there is one coupled cluster approach for the same problem. Here they plot the magnetization as a function of coupling ratio, and you have to find you have to look at the red curves. And basically, they find very much the same. So either a small disordered phase or a direct transition. So this actually makes us quite confident that we are somehow simulating the right physics here. So now let's come to the actual results, back to the octochlore model for the quantum octochlore model. In the following, whenever I show quantum results at t equals 0, we have applied PFFRG. If I show quantum results at finite t, I have applied lambda, PMFRG. And for classical results, I have applied self-consistent Gauss approximation. Okay, as a reminder, this is our model. S are now spin 1/2 operators. And the first important piece of information is that actually the entire alpha beta space is found to be non-magnetic via our methods. But now let's look more specifically at the pinch points. As a reference for later generalizations, let's first of all look at the twofold pinch points. Twofold pinch points, which have this gauge constraints, actually happen everywhere in the classical phase diagram. For example, at this center point here. Now, what are quantum fluctuations doing? The result is shown here. The pinch point is still kind of intact. There is still strong weight here at the center, but it's somehow broadened. But the broadening is actually quite featureless. And this is a typical result for twofold pinch points under quantum effects, which actually in a very similar way we also find for the pyrochlore Heisenberg magnet. And the most straightforward way to interpret this is that, okay, the divergence of the electric field is no longer 0, so kind of charges in the system, which kind of makes sense because in the quantum system, these squared operators cannot all simultaneously yield 0 contribution because these are operators which do not commute. It's actually also quite interesting to observe here that here quantum fluctuations at t equals 0 and classical and thermal fluctuations in the classical model at a suitably chosen temperature, they are pretty much the same, which is also shown here along these ring-like paths. Okay, now let's come to the multifold pinch point. Here at this phase transition, we identified a classical rank 3 gauge constraint. So there are actually 3 derivatives acting on an electric field, which leads to 6 lobes of strong intensity in the HHL plane. And what are quantum fluctuations doing? This is shown here. We observe a very significant broadening of pinch points. So particularly at some inner region, it does not nearly look like the classical t = 0 result. There are actually some soft peaks at incommensurate momentum appearing here. So the broadening is certainly not featureless. Finite temperatures, in addition, makes the broadening even more pronounced. And also here, thermal and quantum fluctuations seem to act very differently. So in the classical model at finite temperatures, there are still somehow 6 lobes visible. And also, we don't see any signatures of emergent photons here. So again, photons would mean that basically an intact pinch point is modulated with Q to some power. So this would mean that if we plot the signal along rings with varying diameter, and we normalize the signal to the maximum along each ring, the signal would lie on top of each other for different ring sizes. Or in other words, if there were photons, then the red dashed line and the blue dashed lines would lie on top of each other, or at least be similar, which we don't observe here. Okay, then the quadratic pinch point. So at this point, we identified a classical gauge constraint where there are now derivatives of different orders acting on an emergent electric field. So this mixing of derivatives has been referred to as a multipole gauge theory and has been associated with type 2 fractons, where all quasiparticles are immobile. And it's also well known that this goes along with quadratic contour lines as we see it here. And now, what are quantum fluctuations doing here? This is shown here. Again, a very significant broadening of pinch points under quantum fluctuations. And additionally, the weight is very much suppressed here at the center of the pinch point. Only if we additionally switch on temperature, then some of the weight comes back here. But there are no quadratic contour lines still visible here, which is actually in contrast to thermal fluctuations in the classical model. So here you can still kind of see quadratic contour lines. So again, here thermal and quantum fluctuations seem to act differently. Okay, and finally a word about pinch line. We observe it here, and we plot the classical pinch line here at a finite temperature to give it a finite width. And pinch line means that if we look at a planar cut, for example, along the pink line, then this contains twofold pinch point. So this is the classical result, and here is the quantum result. So again, a significant broadening of the pinch point and the suppression of weight, and only if we then switch on temperature, some weight comes back here. Okay, I should come to an end, and I also reached my summary slides. So first of all, I find it actually quite amazing what kind of different unconventional pinch points this octochlore model actually contains. And then it seems that we have found some kind of overarching pattern. So unconventional pinch points seem very fragile under quantum fluctuations. So in the context of fractons, this is a bit of a negative message here. We didn't find any signatures of fractons, but maybe we have identified here new spin phases which have nothing to do with fractons, but we can identify their signatures here, which are also measurable in experiments. Then unconventional pinch points are more drastically modified by quantum fluctuations than standard twofold pinch points. And thermal and quantum fluctuations act very differently on unconventional pinch points. And then from the methodological side, I hope I could kind of show you that PFFRG and PMFRG are suitable numerical tools to study these complicated effects. And what's next? We would like to investigate the corresponding XXZ models where we can switch on quantum fluctuations continuously. And that's it. Thank you for your attention.